the source rock is, if it's immature in the oil window, in the gas window, or over mature. And again, we can get ages from the microfossils. If we core into a sealing unit, we can look at the lithology, the type of layering that the unit has. We can take some samples and get vertical permeability measurements. And again, we can get ages from microfossils. Sidewall cores are much smaller. They're typically 1 inch in diameter to 1.5 inches, maybe 1 inch to maybe 2 inches in height. Again, if we're looking at the reservoir, we can look at most of the properties except sedimentary structures, because as we fire the sidewall core into the formation, we tend to destroy some of the fine structures of the sedimentary layering. In the source, we can get the same 4 types of information that we can get with the conventional cores. And for seal, we can get the lithology and the ages, but because of the damage to the formation as we obtain the sidewall core, information on how the rocks are layered and an idea of what the vertical permeability might be is usually not obtainable. And the other type of well samples we can get are cuttings. Here I have a picture of a person drilling through wood, and as the drill goes down, little bits of the wood material comes up. And that's the same type of thing that we get when we drill a well. We have fluids that we have to circulate to try to keep the cutting edges clean and vacate the hole of the sediment particles. And so as that fluid is circulating and the rotary bit is crushing and chomping on the rocks, small fragments of the rock will break loose and it will float up with the drilling fluid. The picture of somebody's hand is holding some cuttings that were collected at a particular well. These fragments can come to the surface as we're drilling, similar to the wood shavings, and they can give us an indication of lithology and age. There's 2 problems, however. The rock is pulverized, so we can't get anything like porosity or permeability or sedimentary structures, and we don't really have much control on the depth from which the samples came. So the little samples of rock that the person is holding in his hand, maybe we know that it should take 2 hours for the drilling fluid to get from the bottom of the hole up to the surface. And so we could back calculate 2 hours ago where was the rotary bit drilling, and we could assume that that might be the depth at which these samples came. But as we're drilling, material is going to slough off and be carried upward along with the drilling fluid. So these little pieces of rock could have come 2 hours ago from the bottom of the hole, or it could have been cavings or pieces that broke off anywhere that we have not yet cemented the well. Some of the common logs are shown here on the top, and the properties that they would measure are down the left side. The red arrows mean it's a major source of information. The green is it gives us some information, not as important. We'll talk about the gamma ray log. We'll talk a little bit about resistivity. The other ones we won't particularly talk about today. The core, as you can see, tells us a lot of good information about lithology, porosity, fluid type, fluid saturation, permeability, and stratigraphy. Some information can be obtained about downhole pressure. That would be from wireline testings and from well tests. And we can get geophysical properties. The sonic log gives us velocity information. The density log gives us the density information. We can also get some information helpful to geophysics from the gamma ray, which is mainly going to give us lithology. and also from the resistivity. So these are the 5 logs that we'll look at today. The caliper, and that's a log that measures how wide in diameter the well bore is as a function of depth. Some lithology logs that can differentiate sands from silts and shales. Porosity logs can tell us something about how porous the potential reservoir units are. Velocity logs, that will give us information that is very helpful for the geophysicists. And resistivity logs, those are important for identifying particular zones that are holding or bearing hydrocarbons. So the borehole size, the main control is how big the bit is at the depth that we're drilling. And we start out with bigger diameter bits and pipes near the surface. And as we go down, we're going to have to use a smaller and smaller diameter. The borehole can also change as the stress state of the rocks change. We can also have some chemical reactions, such as the swelling of clays in shales or dissolution if we're going through a salt layer. And the drilling process itself can impact the actual hole size. We can get a spiral borehole where the drill stem is not perfectly vertical, and the rotary drill head can leave some bit marks, somewhat like the grooves on a bullet that the CSI people love to talk about. So here's a little diagram. The blues are meant to be more shaly, softer sediments. The greenish here could be a harder, more compact layer. It could be a sand, it could be a carbonate. And you can see the well size is larger diameter where the rocks are softer, much less variability and more in line with the size of the drill bit in the harder, more compacted rocks. So the caliper log is the instrument that we use in order to measure how wide the well bore is as a function of depth. And so the instrument, the main instrument is here, and it has a couple of arms that are mechanically pressed out against the side of the well bore, and they have some potentiometers that gives us a measurement so that we can relate the measurement in the potentiometers to the width of the well bore. We use the caliper to understand the width of the well bore as a function of depth, because some logs are sensitive to how big the well bore is, and we can make some corrections if we know there are areas where the well bore is extra large in radius. It can also be used to calculate how much cement we're going to need to cement up the hole. We can also indirectly get some lithologic information because, as I mentioned, the well bore will get wider where we have washouts, and that will indicate that the formations are probably less compacted, less consolidated, or softer in terms of their compaction state. For lithology, there are 2 logs that I'll talk about today. The first is the gamma ray, and the second one is the SP, or spontaneous potential. A gamma ray instrument is a scintillation detector. It's similar to a Geiger counter, and it measures the natural radiation from a formation. Shales have more radioactive particles than silts and shales. And so the gamma ray on the log plot here is the green line, and we have high values close to 100, and we have lower values maybe in the range of 30 to 40. What an interpreter would tend to do is draw a line, a reference line for high gamma values, and that would be called the shale baseline. And so if the green line is near the reference line, the dashed red, the interpretation would be that would be primarily shale. And then as it gets to low values, that would tend to be sands, another thin shale, and another sand. So it's a good way to differentiate between shale and non-shale layers. If I had a silt here, maybe the silt would be represented by these gamma ray values. So intermediate between, say, 35 for the sand and 95 for the shale. The spontaneous potential log works in a similar manner. Here we have an electrode at the surface and then an electrode that we run through the formation as a function of depth. And the voltage difference between the two electrodes is the SP. The way in which the SP log is displayed is similar to the way the gamma ray is displayed, so that if we have values to the right, that indicates it's shale, and if we have values that are further to the left, that indicates that it's sand. For porosity, we have two types of logs that are commonly used. One is a density porosity, and in the display here, that's the solid black line. The other is the neutron porosity log, and that's the red line. The density porosity measures the bulk density or the average density. The neutron porosity measures the hydrogen content. If we have both of these logs, what we can look for is the distance between black and the red curve. If the black is to the right, then it's a shale. If they cross over and the black is to the left and the red is to the right, that indicates that it's a gas-filled sand. So here we have a shale, we have a gas-filled sand, another shale, another gas-filled sand. The red is to the right of the black. And then we have a sand down here, and the red and black are tracking each other pretty much, and that would indicate that it's either a wet sand or an oil sand. And we'll talk in a minute how we can tell whether it's that lower sand has water in it or oil. A log that the geophysicists like myself love is the sonic log. Some people might call it a velocity log. It measures a parameter called delta time, or dt, and so often the sonic log is represented by dt for delta time. We have a tool with a transmitter and at least two receivers. We send a pulse, the energy, the sound waves go through the formation and refract into the receivers. And so receiver one, the shallower one, we start when the pulse is sent, there's no response, and then we get energy that hits receiver one. For receiver two, the same zero time. The response comes in a little later because it's a little deeper, a little further away from the transmitter. We'll compare the start time for the response at receiver one versus the start time for the response at receiver two, get that delta time, and so that's the difference. And if you consider the path to receiver one would be this, the path to receiver two would be this, the only difference between the two paths is this magenta segment, and so that delta time is telling me how much time it takes to travel that distance. That distance is the same as the distance from the center of receiver one to receiver two. So I have a time and a distance, and from that I can calculate a velocity. So delta time is measured in microseconds per foot, and the dt or delta t log is always plotted with the lower numbers on the right increasing to the left. And so it looks like velocity values in terms of numbers or the waveform going from left to right. So it measures the transit time, but transit time is the inverse of velocity. So if I have dt, I take 1 divided by dt, that will give me velocity. And that would be velocity as a function of depth. Resistivity logs measure how much resistivity there is to electrical currents. And typically we'll have 3 resistivity logs, a deep, a medium, and a shallow. And the deep, medium, shallow refers to how far into the formation the resistivity is being read. The deep resistivity measures the formation about 4 feet inside the or away from the well bore. Medium is about 2 feet, and shallow is just a few inches. We usually look mostly at the deep resistivity. If we have high values, and so the deep resistivity is the black, so it's this curve here. If we have high values, that's telling us that we have hydrocarbons, or we might have tight streaks that have very low porosity. If the deep resistivity has low values, that tends to be shale or wet sand, sand filled with water or brine. If there's separation between the resistivities, then the formation fluid is the same as what we are using in our drilling fluid. So if we have an oil-based mud and the two resistivities are similar, then it would say there's oil within the pore space. We could be using a water-based mud for our circulation system. Then if the two curves are tracking each other, it would tell us that it was water wet or brine wet. So let's put all that together. We're going to look at a log. We have the caliper in the blue, the gamma ray in green. We have resistivity, deep, medium, and shallow. And then we have the neutron porosity in red and the bulk density in black. And so all of the logs have been registered, so they're equivalent in depth. And we'll assume that when we drilled this well, we used an oil-based mud. So what do we do first? We'll draw in a shale line on the gamma ray on the green curve. And so here's the highest values. Here's a fairly high value. Here's another high value. And so we can use that to differentiate the lithologies. High values are shale. High value is shale. The intermediate values would be siltstone, and the low values would be the sandstone. So we can break the interval that we've logged here from about 850 feet down to 1,450 feet into sand and silt and shale. Then we can look at the porosity logs and note where the neutron porosity has crossed over and is to the right of the density. This indicates where we have gas. And so here the red is to the right, and so that indicates gas. And so this sand down to about this depth would be filled with, its pore space would be filled with gas. Then we can look at the resistivity logs and see where the resistivity logs have different values. In the gas sands, the resistivities have different values, and so that confirms that it's not oil, since the fluid in the formation, in the drilling fluid is oil. Down here in the lower part of this sand, the three curves are almost on top of each other, and so that tells me the fluid in the formation is the same as the fluid in my drilling mud, and since I have an oil-based drilling mud, I interpret that to be oil. And this sand down here, similarly, they're tracking together. And so the interpretation is that we have an oil sand here and an oil sand here. If these were water sands, the resistivities, the deep, intermediate, and shallow would have different values. They would not track each other as nicely as they are in the oil zones. The other thing that we can do with well logs is we can use them to correlate from one well to the next and build up a stratigraphic framework. So the logs give us detailed information at the location of the borehole. If we have several wells in an area, we can start doing some correlations so we can break out different stratigraphic units. The correlation is based on characteristics of the well log responses, somewhat like everyone's fingerprint has different patterns, and we can use those patterns to correlate which person's fingerprints are on the murder weapon. Often we select a datum, and that's to try to correct for post-depositional structuring and tilting. And so we'll figure out something that we think was at a common depth, and then we'll flatten the other well logs based on that assumption of a particular unit at time of deposition being nearly horizontal. When we start correlating from one well to another, there's two main philosophies. One is to look at the rock units or the lithology, and so we can break out a lithostratigraphic correlation. The other way to do it is to assume what the geological timelines are, so looking for geologically time equivalent units, and if we can do that, that's referred to as chronostratigraphy. Which is better? That's a matter of heated debate. It somewhat depends on your use of the well log correlations. In some cases, the rock correlations, the lithostratigraphy, makes more sense. In other times, the chronostratigraphy makes more sense. So here we have 4 wells, well A, B, C, and D. This could be a gamma ray log or an SP log. The green here represents coastal plain sands and muds. The yellow are shallow marine sands, and the gray is shelf mudstones. And so one thing we could do is we could say, well, I have a really thick nearshore sand here and here and here and here. And so let me make the top of that thick sand a datum or a surface along which I'll flatten all the logs. And then I can start to say, where is the coastal plain? Where are the nearshore deposits? And where are the shelfal mudstones? So this would be a lithostratigraphic or rock stratigraphic. The other way to do it, perhaps I have an index fossil in the coastal plain sediments that occurs here and here and here. And then I'm going to just project out. And now I'll hang or reference the wells based on that index fossil, which I'll assume is a timeline. And now I can correlate the coastal plain, the nearshore, and the shelf. And these horizontal lines would be boundaries between different episodes or pulses of sedimentation. Using some terminology from Van Wagner and et al., this would be one parasequence, this would be the next, this would be the third, this would be the fourth. So it's 2 different ways to take the same data and come up with a way in which to relate the rocks in one well to the rocks in the other 3. Does this really matter? I've referenced the 4 wells back to true depth in the upper and the lower. I've drawn in the correlations based on the lithostratigraphy from 2 slides ago and the chronostratigraphy from the previous slide. In terms of trying to find fields, there's probably not much of a difference, so the explorationist wouldn't be all that concerned. However, if we're in a field production stage, then things might be important. As an example, let's say I wanted to inject some gas in this lower sand in the B well. If the lithostratigraphy is a better representation, then I'd be pushing hydrocarbons and producing it out of the 3rd sand in well C. But if a better way to correlate it is the chronostratigraphic method, if I inject gas in the lowest sand in B, it will push oil or gas into the 3rd sand in well C as opposed to the 2nd sand. So when we get into field production, the ways in which we correlate things become important. And we've discovered that the chronostratigraphic way of doing correlations is more effective in explaining production than is the lithostratigraphic formation method of correlating. And we'll talk more about that in a future lesson. Here's an example from Louisiana. I have 1, 2, 3, 4, 5 wells. I have some environments that are shown down here. This is reddish stuff is supposed to be the orange stuff. The yellow is shallow marine sand, so those are my potential reservoirs. And we can do a chronostratigraphic correlation. This was done by Van Wagner and his co-authors and published in 1990. And so we're starting to build up a stratigraphic framework for this particular, I believe this is a single field. A second example, this is from East Texas. We have the Austin Chalk, which is the carbonate-looking formation at the top of the 4 wells. There's more carbonate down at the base. This is the Buda limestone. And in between those 2 carbonates, we have a clastic section with sands and silts and shales. And well A has 1 sand, B has 3, C has 3, D has 1. One way to correlate them, those sand bodies would be something like this. Another possibility is to correlate them something like this. The question is, I'll go up a slide, is this a better way to correlate, or is this more reasonable in terms of the geology? In this area, we have a seismic line. Here is the position of well C and well D. And, oops, sorry. The package that we were looking at with the clastics is the one that's not dimmed out with the gray. And you can see that the seismic reflections are dipping down to the right. And so they suggest that this type of correlation is probably more reasonable. Now here's the same cross section. Now it's referenced all the wells to true vertical depth, so 12,000, 13,000, 14,000 feet. Here are the sands, and there is a gas sand in the North Oaks field, this first sand. It waters out by the time I get to the second well. This well is wet. These sands are wet. But there is a field, a gas field, the Hortense field, that is in between these 2 guys. And if I correlated the sands as I did on the first slide where things were more flat-lying, I would not be able to explain the existence of this Hortense field. The Hortense field was drilled after these 4 wells, and so somebody was either very technically savvy and realized he had a stratigraphic trap there, or somebody was extremely lucky. And one of the adages in our industry is, I'd rather be lucky than technically correct. There is an exercise with exercise 4. It has, here's the base map. It has 5 wells, and there are resistivity and SP, I think it is, or gamma ray, I can't quite remember now, logs. And your task is to use the 5 wells, cut them into individual strips, and then try to do a correlation using a well character fingerprint type method to correlate from well 5 to 4 to 3 to 2 to 1. So I don't have time to go into exercise 4 anymore. This is kind of the teaser. So that's the end of my prepared remarks. We've worked now down through lecture number 4, well data. Thursday of this week, we'll have lecture number 5 on seismic data. Then we're going to have a 2-week hiatus. I am unavailable next week. And then in 2 weeks, Tuesday is the 4th of July, which isn't a good day to have a webinar. And then I am unavailable on that Thursday. So our next session after Thursday will be Monday, July 11th. We'll talk about seismic reflections. July 13th, we'll talk about source rocks. And then you can see the rest of July will cover the first column of these 34 different units. So with that, I'll turn it back to Danielle for some questions.
Great, thank you, Fred. We have a question that came in already. What is the geophysical aspect of the resistivity log?
The geophysical aspect?
That's the question.
The resistivity is usually used primarily for hydrocarbon detection. And so offhand, I cannot think of a real geophysical application other than it's important for an interpreter to know where his or her hydrocarbons are located.
Okay, great. That was the only question that we had so far. I don't know if you want to wait maybe a minute, but
and if there's a question on previous weeks or previous lessons, that's fine as well.
Okay. Okay, we got a question that came in. Will EM data replace seismic when tying to wells?
EM is electromagnetic.
That's
and
what I was. Yeah. Oh, sorry. I thought that was a question.
No, I was trying to clarify it for those that were listening in. EM data is relatively new. It is a much lower resolution than seismic. And so I have not seen EM data used without tying it back to the seismic data. So they work very well hand in hand. Certainly we can use seismic without electromagnetic data. It would be difficult for me to envision using EM data without having the seismic to understand the context within which you're trying to interpret the electromagnetic data.
Great. We had a question about, can you explain more about how to obtain chronostratigraphy correlation, please?
Yes. We'll talk about that more in some of the future lessons. Let me see if we will talk about that when we get into the stratigraphic hierarchy and seismic sequences. It turns out that seismic reflections tend to parallel the chronostratigraphic correlation lines as opposed to the lithostratigraphic. One way in which to try to get the geochronological lines is to use fossils, first occurrence, last occurrence. We may have some sort of a unique bed, like an ash layer, that we can assume is chronostratigraphically significant, a small moment in geological time. The other way in which we do it using well logs is we do the character match, usually in shales, and that's what exercise 4 focuses in on. And the similarity in the logs from one well to the next we will use to try to establish possible chronostratigraphic markers, and then try to build a chronostratigraphic framework using that well signature correlation.
Okay, we have another question about, it says, what about the FMI logs and dip data? How do they work and what are they used for?
I think my depth of experience with FMIs are not enough for me to want to delve into that.
Okay.
So I'm gonna hit the pass button on that one.
Okay, no worries. How do fault/discontinuities at the subsurface impact the reliability of wireline logs, like porosity logs?
Can you repeat that for me?
Sure. How do faults or discontinuities at the subsurface impact the reliability of wireline logs, like porosity logs?
Well, if you have discontinuities near the surface, Hopefully you're able to co-register all the logs that you're trying to correlate so that you have something at depth that you can assume is reasonable to flatten on.
Okay. We have another question. How would you know if the values from a sonic log are erroneous? Like, how do you know that it's real data?
Yes, with the sonic log, and I think we'll talk about that in a future lesson. We do have to worry about editing the logs, and there is a thing called a cycle skip. Let me see if I can get to the right slide. So I said that the thing that we measure is when the energy first gets to receiver 1 and when it first gets to receiver 2. Let's say with receiver 2, the first response isn't that big, and the detection algorithm that we're using doesn't pick this as the first response, but picks this as the first response. So that delta T would not be measured here, but it would be measured here. So it would be way too much time. And so if we have a cycle skip, as we look at the log, it will be a very anomalous outlier. And so people can usually visually recognize where cycle skips have occurred, and then they will just edit through it or delete the bad point.
Okay. Can a low resistivity also mean that you have a high porosity?
A low resistivity. Yes, I believe that is right.
Mm-hmm. Yeah, I'd agree with that. What criteria do you use to define the shale baseline?
The shale baseline, usually, I'm trying to remember which way to go. What we'll look at log itself and see where the maximum values tend to fall. And if I can get the one where we put them all together. So here's the 0 to 100 for gamma ray. The biggest values look to be just over 50. And so in this case, the shale baseline was drawn in the position of 50 on the 0 to 100. So it depends on how much radioactive material is in the shale, and if it's got a lot of radioactive material in it, it'll be closer to 100 or maybe even more than 100. If there's not that much radioactive minerals within the shale, then it might be 50 or even less. So it's all on a relative basis. We look for what tends to be the bigger values and attribute that to shale, and then things that are significantly less than that would be built and the sand.
Okay. What is the difference between a sonic log and VSP data?
The sonic log measures interval transit time, that delta T that I was talking about. A VSP is a geophysical experiment we do when we have a well bore. We will have a surface seismic source. Let's say we drilled offshore from a rig or a platform. We could lower an air gun off the side of the drill rig, and we would lower geophones down into the well bore at 7,000, 8,000, 9,000, 10,000 feet. We would fire the air gun, and then we would listen for how long does it take the energy to go from the surface down to 7,000 feet, how long to 8,000, how long to 9,000. And so if the geophones in the wellbore are separated by more than about 500 feet, we call those check shot surveys or velocity surveys. If the geophones are more on the order of 50 feet apart or 25 feet apart, then we call it a vertical seismic profile of ESP. And again, we'll talk about well seismic ties in lesson 15. We'll talk about check shot surveys, and we'll talk about VSPs.
Great. I think you've pretty much, a lot of these questions are related to like sonic logs and different things, and I feel like you've answered them in relationship to like velocity model building. And also there was a question about how this may relate to tomography. I don't know if you want to answer that.
The tomography is a very specialized set of data processing, and I think it's really beyond the level of this course.
Right. Okay. Yeah, I think you've pretty much answered everything that I'm looking through the questions.
Okay.
So yeah. All right. Well, great. Well, with that, thank you everyone for attending. Thanks, Fred, again for giving this lecture, and we look forward to seeing you on Thursday. Take care, everyone.
Thanks for tuning in.
Thanks.
Bye-bye.
Bye.